Bismillahirrahmanirrahim. I'll be discussing Anfis today, Adaptive Neurofuzzy Inference System. And this is primarily a representation of a fuzzy system in a neural architecture. So we'll be discussing some of the details about neurofuzzy systems. Now, there are multiple ways in which neural networks and fuzzy logic could be combined together. Neural networks and fuzzy logic are two complementary technologies. That means that neural networks are primarily used to model the learning behavior of living beings, whereas fuzzy logic is a technique that focuses on modeling the reasoning ability. Okay, so if you combine neural networks and fuzzy logic together in different ways, you will actually be combining the learning methodologies and the reasoning methodologies together. So what we'll do here is that we'll just talk about a neuron and how these different neurons can be connected together in order to form a fuzzy rule-based system. So this is what the neurofuzzy architecture that we'll be discussing today will consist of, and especially Anfis. So what happens? What's the advantage of combining neural networks and fuzzy logic? The advantage of combining neural networks and fuzzy logic is that by combining these two methods, one of the objections that comes to neural networks is that it's actually a black box approach. So you can't really see what's happening inside. So therefore, these explainable neural networks or explainable machine learning is the area that has actually come across these days. Another way of explaining what's happening within a neural structure is to actually incorporate a fuzzy architecture within a neural structure, and this is what we'll be discussing today. There are numerous ways in which neurofuzzy systems can be developed. First method of developing a neurofuzzy system is that you embed a fuzzy rule in a neural architecture. So different layers represent the different stages of implementation in a fuzzy rule-based system. Then you can have a fuzzy rule-based system that could be constructed as a reinforcement learning-based learning approach, where you actually modify the rules or extend the rules in a way through some sort of reinforcement, and that reinforcement is done through a neural architecture. Then you can also have like a neural network constructed through a fuzzy partitioning of the input space, and one of the examples of this was discussed in the last lecture, where this grid partitioning approach was discussed that could be used to generate fuzzy rule base. So the overall idea of having adaptive neurofuzzy system, adaptive neurofuzzy inference system is that we want to generate rules automatically. When we say we want to generate rules automatically, that means that all the parameters that define a fuzzy rule-based systems are determined automatically and they are optimized. Okay, so this is what Anfis is actually doing. Okay, so you all know what a neural architecture is. Neural architecture consists of neurons. These neurons are connected together with the help of through some weights, and the information flows from one neuron to another neuron, and is weighted. Every neuron may have multiple inputs that are coming in, and then a weighted average of those inputs is taken, and then some sort of thresholding is done, and that thresholding is done through some activation function. And the information flows from the input neurons to the output neurons, and output neuron site Q, but then you calculate the error. You have some sort of a function that calculates the error, and then that error is minimized with the help of some gradient descent algorithm, or least squares, or some other optimization algorithms are actually used. Okay, so typically today we'll be talking about neurofuzzy system, and especially Anfis. So Anfis it's actually a 5-layer neural architecture, which is called Anfis. And what are these layers? We'll discuss these layers in detail in the latest slides. But let's say you have layer number one. So layer number one would consist of the inputs. So you have the inputs that are coming in. That is layer number one. So let's say you have got some linguistic variables, for example, temperature, pressure, height of a person, different types of linguistic labels that you can, linguistic variables that you can define, and that would consist of your first layer. Okay, so primarily the first layer is actually doing nothing. It's primarily just like the input layer of a neural network. So there is no transformation being taking place here. There is no thresholding or activation being done at this layer. So this is basically a layer that collects all the inputs together. So suppose in this architecture you have T and H that are the inputs that are coming into your input layer, and that's layer number one. Okay. Then you have layer number two, and that layer number two consists of the input membership function. So here you have layer number two, which is the input membership function. So input membership function layer, this box or this neuron here is actually representing an activation function. So whatever comes in to this neuron, that on that particular input, some sort of activation is applied, and that activation you already know is applied to some sort of an activation function. In our case, because we are talking about a neuro-fuzzy architecture, that activation function would be a fuzzy membership function. Okay, so here in each of these boxes, you have an application of fuzzy membership function. So you have some input that comes in, then you have a fuzzy membership function. Let's say if it is Gaussian, so the input comes in, you have a Gaussian membership function, and then you find out the membership value of this. So the output of this particular neuron, is a fuzzy membership value. So here you have a fuzzy membership value that is coming out of this particular input. Okay, so these are the fuzzy membership values that are coming out. So that is layer number two. So layer number two is primarily an input fuzzy membership function application, or in other words, input one and input two together. This process is what we have discussed as the fuzzification process. So these two layers comprise of the fuzzification part of a fuzzy rule based system. ठीक है, आपके पास inputs आए, you have processed those inputs, passed them through some activation function, and then that activation function or membership function is applied on that input, and as a result you get some value, some membership value, and the output of the second layer is the membership value of your respective inputs. So in other words, ये जो layer है, this is actually representing different linguistic labels, right? Then you have the third layer, which is here, and this layer is primarily a fuzzy rule layer. A fuzzy rule layer would mean that, let's say you have got input one and you have got input two, you have fuzzified those inputs, and at this level these inputs are combined together. For example, this neuron here is doing a combination of a fuzzified T input, then a fuzzified H input, and there could be multiple inputs that are coming in. So all these fuzzified inputs that are coming in, all these fuzzified inputs are passed through layer number three, which is a fuzzy rule layer. A fuzzy rule layer could consist of, or this neuron could perform a process which is what you call as the say the application of the T norm or the S norm operators. Okay, so if there is an AND connection between two variables, two linguistic variables, then this node would represent the implementation of AND. It could represent the product of those two membership values, or it could represent min of the two. Okay, so this layer here is primarily doing what? This layer is primarily applying the fuzzy inference on it. If you remember the fuzzy rule based systems, the steps for fuzzy rule based systems, the first step is the fuzzification step, the second step is the inferencing step. So the fuzzification step is done at layer number two, and the inferencing step is done at layer number three. And we'll just see an example later, जिसमें इसकी further details के बारे में हम बात करेंगे. And then you have layer number 4, and this layer number 4 is the defuzzification or the output membership function application. So the output membership function application is what consists of layer number 4. Layer number 4 and 5 together, they may represent the defuzzification process. Okay, these two layers together may represent the defuzzification process. So the output that you get from layer number 3, which is the inference, that is passed on to the membership function of the output, and then that value, the reverse of this process is actually done. If you remember the fuzzy the inference system, so defuzzification process you have to pass over. So layer 4 and 5 together may represent the defuzzification process. So this is how the Mamdani's model is actually represented here. So let me just repeat this again. So layer 5 is primarily the final defuzzified output that comes out, and that is actually represented by D. Okay, so let me just repeat this. The first two layers here, are representing the fuzzification process. This is representing the inferencing process, and this is representing the defuzzification process. And this is exactly those steps that are studied in fuzzy rule-based system. Okay, so let's take an example. And here we are not talking about Mamdani's model, we are talking about Savannah's model. So let's suppose we have got these two rules. The first rule is that if x is a1, where x is a linguistic variable and a1 is a linguistic label that is attached to x, and y is b1, and then the output is a polynomial. So this is a first order polynomial. Similarly, you have rule number 2, which says that x is a2 and y is b2. Then you have f2, which is another first order polynomial. So these are the two rules. Let's try to develop an inference structure for these two rules. So remember, these are just two rules which are given here. We'll develop the inference structure. Before we actually do that, let's just revise a fuzzy rule-based system in the Sugano model. So here is rule number 1, which says that if x is a1, and so there is an and connection between the two, y is b1, then, and because there is an AND connection here, so W1 would primarily be min of the membership values of A1 and B1. So this is the min operation that is being done here. And then you apply the polynomial, you get F1. And then similarly, rule number 2 is applied. You have X is A2 and Y is B2. And again, there is an and here. So this W2 is representing what? This is again representing a T-norm operator, or the product operator or the min operator. And you also find out F2. So then these W1s and W2s are combined with F1 and F2 to find out the overall aggregated output. The overall aggregated output is actually calculated in this particular case. Okay, so from X you find out the membership value in A1. This is what you call as the defuzzification process. So fuzzification process. So here from Y you calculate the value of B1, which is again a fuzzification process. Then you find out the value of W1, which is through the T-norm operator, which is the inferencing process. And once the inferencing process is done, then you find out the weighted average of the polynomials. So this is how these two rules are represented. So if these two rules are represented in the form of a neural architecture, then this is a neural network that will be generated. Okay, here you have the inputs, and these inputs are represented by, let's say, X and Y. These are your inputs. The first rule says that if X is A1, so if X is A1, so this node here is representing A1 membership function. So if X is A1, the value of X goes into this layer, into this neuron, and the output here will be a membership value. Okay. Similarly, what is it's connected to? It's connected to Y is B1 through an AND operator. So here you have Y and here you have B1. So Y passed through B1, you get another membership value for here for Y. So you get a membership value for X here, you get a membership value of Y here. And this node here, which is layer number 2, this node here is representing what? This is representing the product node. The product node, what is this product node representing? This product node is primarily taking the product of these two membership values. Remember, product of these two membership values is a T-norm operator for AND. You can take the min of the two membership values that are coming from this evaluation and for this evaluation. For x is equal to a1 and y is equal to b1, और इन दोनों को use करते हुए through an AND operator you can either take the minimum of the two or the product of the two. Okay, so you get these values and this is what W1 is representing, mean of the two or the product of the two. Similarly for rule number 2, rule number 2 में आपके पास x is a2, so this is the route that x would follow, pass through an a2, you will get a membership value of a2. Similarly y is b2, so you apply b2 on that, find out a membership value, and here at this node you are actually taking the t-norm operation of the two, right? The t-norm operation of the two is done here and you get a value of W2. These are the weights that you get after applying the t-norm operators for layer 1 and layer 2. Okay, so layer 2 gives you what? Layer 2 gives you the weights of each of the rules, okay? And then they are transferred to your input. Remember, in case of Sugano's model, weighted average निकालते हैं. So weighted average W bar, if you go to the previous slide, you will see कि यहाँ पे आपके पास ये W bar represented है. This W bar is calculated, ठीक है? Here W1 bar and W2 bar are calculated, and from this formula you can easily find out कि W1 bar or W2 bar क्या है. So W1 bar is W1 divided by the summation of W1 and W2. So this would be W1 plus W2. So summation of W1 and W2. This is what W1 bar would represent. Okay. So this is what you call as the W1 bar. Okay. So you have W1 bar here. और W2 bar में simply इसको हम W2 से replace कर देते हैं. You get the W2 bar. Okay. So you get the W2 bar out of this. So these two W1 bar and W2 bar are calculated, और F1 and F2 से आप respective को multiply कर देते हैं and you get your output. Okay, so this is what you are getting here. You calculate the values of W1 bar and you calculate the value of W2 bar. You take the product with F1, that gives you one component of your output. You multiply it with F2, that gives you the other component of your output, and then a simple summation is actually done to get a complete output of your network. So this is how this network or this neural architecture would look like. So what is your first thing here? The first thing is your input. Layer number 1 in this particular case is representing the membership values, or these are the membership functions that are applied here. Layer number 2 here is representing the t-norm operation of your membership values. Layer 3 is normalization of your weights. Layer 4 is finding the output, respective output of each rule, and then you have the summation, which is combining all these rules together, output of all these rules together. So this is how an Anfis architecture would look like, and this is, remember, for 3 rules only. Now if you have another rule here, let's say कि अगर आपके पास कोई z input भी आती है और आपके पास let's say कि यहाँ पे आ जाता है, if it says and z is let's say a1, so we also have, let's say z is a1, so मेरे पास I can add an input z here and then it goes to a1, so it could go here straight away, and then you can find out the membership value, and the rest of the process is same. So यहाँ पे आपके पास yeah, so you can actually यहाँ पे a1 आ जाएगा, not there, a1 यहाँ पे आएगा आपके पास, and then this goes into that a1, and then the product is taken because that is rule number 1, so it actually goes to the product in this particular case. ठीक है. So अगर आपके पास कोई एक और input आती है, तो you add another input here, you add the membership value of that input, and then you add it to the respective t-norm operator of a particular rule. तो अगर वो rule 1 का हिस्सा है तो that comes here, अगर वो rule 2 का हिस्सा है that comes here. So this is how another input would be added. For example, z will be added here, it would go to another membership values. Let's say कि यहाँ पे भी हमारे पास a3 है, let's make it a3, और इसकी जो output आती है, let's say if it is part of rule number 1, तो यहाँ पे it says कि and z is A3, ठीक है, so if it is अगर rule number 1 ये हो, if x is A1 and y is B1 and z is A3, तो z is A3 would go to rule number 1, so it would go here. और यहाँ पे जो W1 कैलकुलेट हो रहा है इसके अंदर weighted average of z भी आ जाएगा, तो this is for the third input. So let's say कि आपके पास जो है वो मल्टीपल इनपुट्स हैं और मल्टीपल आउटपुट्स हैं, so you can actually modify this architecture accordingly, right? So just to recap, if this is the rule at the top, then this part here will be representing x is A1, this link here is representing y is B1, this node is representing the AND operation between the two, which is the t-norm operation. Then this layer is primarily representing the weighted average of the weights that you have, so weighted or the average weights, and then here the respective outputs of each rule is calculated, and finally these respective outputs of each rule are combined together to find out your overall output. Okay, so layer by layer, this is what is happening. This is layer number 1, where you apply the membership function and find a membership value mu. Layer 1 finds the parameters or the membership values of your input. So this is part of your fuzzification process. Layer number 2 is the t-norm operation that is done, and as a result of applying this t-norm operation, you are calculating the weights W1, W2, W3 as in Sugano model. Then you have layer number 3, which is calculating the normalized weights, firing strengths of these neurons, or the normalized weights, which are represented by W1 bar, W2 bar, W3 bar, and that is calculated at layer number 3. And layer number 4 will calculate the respective polynomial for each rule. So the first block here is representing polynomial 1, and the second block is representing polynomial 2. You calculate these two separately, and here the aggregation of these is actually calculated. Okay, so if you have an architecture of an Anfis architecture with two inputs, then two inputs and three linguistic labels for each input. So if you have x and y, and x could be divided into have three linguistic labels. X could have A1, A2, A3, and y could have B1, B2, B3. Then the possible number of rules that you can get out of this are 9. So you can have 9 separate rules, and this is the neural architecture against these 9 different rules that you can have, right? So this, as I told you, this is your input layer, this is your membership function layer, this is your t-norm layer, this is your weighted average or weighted normalized weight layer, and here you have the output of each of these rules, and here the output of each of the rules is primarily aggregate. So this is what the Anfis architecture would look like. Similarly, अगर आपके पास 2 inputs हों और 5 linguistic labels हर input के लिए हों, you can calculate an architecture. Remember, layer 2 and layer 3, they are fully connected. That means that every input coming out of layer 1 goes to every neuron which is present in layer number 3. So layer number 2 and layer number 3 are fully connected. That means कि यहाँ पे इस न्यूरॉन की जो आउटपुट है वो यहाँ पे हर न्यूरॉन के पास जा रही होगी, लेयर 3 के हर न्यूरॉन के पास जा रही होगी, एंड सेम इज द केस फॉर द सेकंड वन हियर, विल गो टू एवरी अदर न्यूरॉन, क्योंकि आपने यहाँ पे नॉर्मलाइज. सो रिमेंबर, ये सुगैनो मॉडल की रिप्रेजेंटेशन है. सो दिस इज रिप्रेजेंटेशन ऑफ सुगैनो मॉडल. Okay, so this is some say discussion on how this optimization is done, but the idea of adaptive neurofuzzy system was proposed in 1997 by Zhang et al. The name of the paper was Neurofuzzy and Soft Computing, and this was actually implemented for a function that is represented here by Z. So Z function के ऊपर उन्होंने they implemented this, and the range was like from -10 to 10, in which the value of x and y could vary. There were 4 input membership functions for each of x and y, so that would mean that there would be 16 total rules that were actually implemented. These were the membership functions that were used initially, and after applying the Anfis, the lower membership functions were obtained. These were the trained membership functions after 100 iterations. This is the training data representation and the Anfis output. The training data and Anfis output, and you can see that they are very closely matching each other. Root mean square reduce over continuously. It's almost continuously reducing. So that means that it's actually being converged. Okay, here is another example. Here you have 2 rules, A1, B1, A2, B2 are the membership functions, and the 2 rules are given right at the top of the example. So you need to, and the 2 polynomials F1 and F2 are also given. So you need to find out for x is equal to 3 and y is equal to 4, we need to find out the value of our output. So you can solve this using a fuzzy rule-based system, and you can also try to develop an Anfis architecture out of it. And I'll leave this as an exercise for you. So you can try to solve this example yourself and then come up with some answers. Okay, so here is another example of an aircraft trajectory data set where Anfis was actually trained. What I can simply tell you that here the idea is that you have some autopilot features which you want to train. उसकी जो aircraft की जो trajectory है, that is something that you want to learn. Or there are various inputs. It's a time series sort of an application जिसमें you are taking the inputs at various time intervals, or then you are concatenating them for a given interval, and then you are using that input to train. For example, the height of the aircraft at time t is taken then at time t minus 1, t minus 2, t minus 3, t minus 4. So you go into the history, and then you concatenate all those values, and then you feed them to your Anfis architecture, and then you try to learn इस वक्त given this height what should be the speed of the aeroplane. ठीक है. So that sort of an application is this. Okay, so just to tell you that how accurate this is, this is just after one epoch. The solid line is representing the actual trajectory, whereas the dotted line or the line with the red dots is representing the Anfis prediction. So these predictions are not very good. The trajectory which is given is not properly matched. But if you go for 100 iterations, then you will see that it starts matching, especially in the middle and towards the end. And if you go with some change in the input membership function, so this was with 2 membership functions for your 4 inputs. So every input had 2 membership functions. Here there were 4 inputs, but there were 3 membership functions. So you can see that अब उसकी जो learning है वो पहले से काफी बेहतर होती जा रही है. And if you increase the number of inputs, that means that उसके अंदर आप time series भी डाल दें. तो time series डालने से क्या होगा कि आप previous values को भी देख रहे हैं. So 4 inputs से आप increase करके 6 inputs पे लेके जा रहे हैं, और membership function को आप 2 पे लेके आ रहे हैं. So after just one iteration, you can see that how accurate predictions or how accurately the system has actually learned. Okay, so this is the result of the training, but you need to test it on validation data set in order to find out whether the training has been effective or not. Okay, so that's it regarding the Anfis architecture. I hope you got the basic idea of Anfis. In our next discussion, we'll talk about some other architectures in which neural networks and fuzzy is